Hello my wonderful students and welcome to the lesson on 4.64 geometry. This is Mr. Wagner in his radio voice describing to you what's to come. Here's the vocabulary for this lesson. Make sure you understand it by the end of this lesson. Also use the extra examples in your book for additional help with your assignment. Anyway, here's 4.6. Okay, so isosceles, equilateral, and right triangles. What do we have here? We have, if you remember, this is an isosceles triangle. What makes it isosceles? Let's add some stuff here. So this is original stuff here. I'll add it in black. This side is congruent to this side. It has at least two congruent sides, and I didn't need that. That just made it look worse. Oh, there we go. Okay, so this and this are the same, and you can prove some other things about isosceles triangles, but we're just going to say that that is true to start. So what is true about these things? Well, this right here is called a leg of the isosceles triangle. This part right here is the leg. Let me color code just to make that a little easier to see for you, I think. So here, that's not what I want. Let's try that. Blue, there we go. So this is a leg right here. And this is also a leg right here. So if you have an isosceles triangle, these things are called the legs. So this is also a leg. So I'll label that here, label that on your picture too. And then these parts, this is going to be called down here. This is called the base. So does the base have to be on the bottom? No. Let me kind of show you what I mean by that. So could I spin this around and is the red part still the base? Yes, these two are still the legs. They're the equal parts, the congruent parts, and that's the base. But for right now, it is on the bottom. But it doesn't have to be on the bottom, just so you know that. And so this is called the base down here. We're going to learn some stuff as we move on about the base angles. But for right now, these are right here, this one and this one. We're just going to label those as the base angles. So these are the base angles. I'll use my shorthand for angles there. These two things are the base angles. And so what do we know again about isosceles triangles? Let's write down what we knew from lesson 4.1. We knew that isosceles triangles have at least two congruent sides, and then this picture goes along with these kinds of triangles, or if a triangle has exactly two sides being congruent. So let's write it down like this. If a triangle has exactly, so isosceles has at least, but if a triangle has exactly two congruent sides, then it can also be labeled as shown here. So like this, it can be labeled like this. If it has more than two, which would mean it has three congruent sides, then we can't call one side the base and two other sides the legs, and we don't have that going on. But let's move on to another idea. And so we got some cool buildings, sculptures over here dealing with some triangles. This right here is going to be the base angles theorem. Now I'll use my abbreviated terms here. The base angles theorem. This is theorem 4.6, and let's just start with this one. So the base angles theorem says take out your different colors, take them out now, take out those different colors. Okay, and let's start with here, this is in black, so we're going to start with an isosceles triangle, and it has just two congruent sides. We're starting off with that, so we start with this. What can I say from there is also true? This is the base angles theorem, so we're probably thinking out something about the base angles. We can say that this is true. I can add this into the picture. I'll do that in a different color here. Please do the same in a different color. So what does it say? base angles theorem, or theorem 4.6, says that if you have two sides or two legs, you could even say, but the two sides or legs of an isosceles triangle being congruent, so they are congruent, this, I'm going to circle this and say this statement implies that this statement is also true, that you have the base angles are congruent. So the base angles are congruent. Now, does this work in reverse? What do you think? If the base angles are congruent, let's do that here in this picture. So let's put that in black or in pencil with yours. So if that's true to start, let's write that down over here underneath that. The base angles are congruent. Do you think that implies this other part, the two sides of an isosceles triangle, are congruent? So if these are congruent, does that mean that this has to be true? Different color, different color, different color. Here we go. Does that mean that this has to be true? Yes, it does. So that's what the theorem says, that I can reverse this, and I can now say the two sides of an isosceles triangle are congruent. So that's the reverse of this, or in other words, I switched the hypothesis and conclusion. Do you remember what we call that? If you say converse, you got it. So this is the converse of the base angles theorem. So it's still a theorem. There we go. It's just the converse of the original theorem. So it's theorem 4.7 if you wanted to use the numbers, but I'd much prefer you to say converse of the base angles theorem, and over here base angles theorem if you're using these two theorems. So you can start with this being true and say the base angles are true. You can start with the base angles being true and say that the legs are congruent. And then let me show you something pretty cool. So this is in San Francisco. This building is called the Transamerica Pyramid. Maybe you've never been to San Francisco, and maybe you've never used this program, Google Earth. So this is actually something you can utilize, you can use. So I was driving down this road earlier this summer, actually. I was on a road trip and coming back from hiking on the Pacific Crest Trail, and I remember this very well. I was driving down this road, and I'll be your tour guide now. Hello everyone, and welcome to the tour of San Francisco. We're currently driving across the Golden Gate Bridge, one of the icons of San Francisco. We're going to make our way over to Alcatraz Island next. Here we are. I'm just going to pan around here, okay? And here we go. You can see the wonderful coastline of San Francisco, and over here we are at Alcatraz Island. All right, so let's make our way here. And also now we're moving into downtown San Francisco. You can see some of the lovely piers that we have. And here we are at the Transamerica Pyramid, San Francisco, California, 94111. Okay, so that's a really cool program. You should check it out sometime. If you've never checked out Google Earth, you can basically zoom into any place in the whole country, tons of places in the entire world. You can zoom in and check out cities in a three-dimensional view. You can go to Street View and see what real pictures look like from that. Maybe I'll even click on this. And so this was a picture that somebody took at this very spot in San Francisco. Very cool. But let's go not back to that, but back to this. You are hopefully using this to help you watch or go to that to watch the videos here that we have. But the base angles theorem, converse of the base angles theorem, using some isosceles triangles. You can see the isosceles triangle face of this side of the pyramid. Pretty cool that they used isosceles triangles in that. So don't copy these pictures down yet. Don't do it. Don't copy these pictures down yet. I just want to show you something first. Fire Marshal Bill, is he coming back? Let me show you something. Yes, let me show you something too, Fire Marshal Bill. Fire Marshal Bill. Okay. So don't copy these down. I want to show you something pretty cool. I can just take this. Do you think this is going to hold true if I have an equilateral triangle? Do you think it's also going to be equiangular? So based on what we just said back here, this has to hold true because equilateral triangles are just special types of isosceles triangles. So I can take this and I'm going to superimpose it over here on this one and line it up as good as I can there. Boom. Okay, so that and that can kind of come together. If you have one or the other, you can assume that the reverse of it is true in a sense. So now I do want you to copy down this picture. Alright, so let's copy this down right here, and we'll make this is a corollary to the theorem. Whoops, didn't mean to do that, but this is to change the color there, this is a corollary to the theorems we just learned about here. So a corollary to 4.6 and corollary to 4.7. Basically all it says is this: if you have an equilateral triangle, which I'm going to abbreviate, I'm just going to abbreviate using a symbol for triangle. I'll just say that if this is true, that implies that this is true. You have an equiangular triangle. And if you have an equiangular triangle, that implies it goes the other way, reverse direction. It's a biconditional statement in a sense. Equilateral implies equiangular, equiangular implies equilateral. So you can work both ways with this. This is the corollary to theorem 4.6. So let's write that down underneath that one, and this is the corollary to theorem 4.7. So kind of special stuff about equiangular triangles. If you look over here, this picture, you look at it long enough and it'll just start to like make you go a little loopy, because this isn't really a possible way to have this. Try to make that lay that down on your floor, make a picture that looks like that. Look at it long enough and you'll understand what I'm talking about. The Bermuda Triangle, very famous triangle geography wise. It's essentially an equilateral triangle, but very dangerous flying zone. It seems like a lot of planes go down in that area. And bringing out the nerd in me, I love Zelda, the game Zelda. And so this is Zelda, or this is Link. Zelda's the chick that he saves in the game, but this is Link holding the Triforce. That's his source of power, you could say, in the game. And equilateral triangles within that right there. I'm not a huge gamer, but I've always enjoyed the Zelda games. I've always enjoyed the Madden games. I've always enjoyed a few other games too that I just can't. All the Mario games. Mario Kart, awesome. Mario Kart is sweet. I love Mario Kart. But anyway, let's look at these right here. So take your colors out. Let's just use our pencil for right now, though. I'm going to say that this stuff is true to begin with. So I'm going to tell you that this side and this side are congruent. I'm going to tell you that this side and this side are congruent to each other, and they're also congruent to these. So they all have the same number of marks. And this one's going to be 75 degrees. This is going to be x degrees. This is going to be x degrees. And this is going to be y degrees. Okay, so now take out your different color and let's add some things in here that we can say are true. So what could I say in this triangle that would be true based on what we just talked about back here? Based on either this one or this one, the base angles theorem, because I see some isosceles triangles there. Well, I notice that the two sides are congruent. That would tell me that the base angles are also congruent. And so over here I've got, these are the two sides are congruent. That would tell me that this angle and this angle are the same. This one's called x, so this one should also be called x. I could call it the same thing. Same thing over here. This one's called x. I have two congruent sides, so I have an isosceles triangle. That would mean this one would also be x degrees. And this matching up, that should be like, yeah, that makes sense. Because what kind of angles are these? These are vertical angles. So this one should also be congruent to this one. So that lines up like it should too. So if you didn't use a different color and you look at this later, it doesn't make any sense. I need to see the different color here in your notes, and we could say something like this, that the things, let's write this down, I think it's important, the things added in a different color are true by the base angles theorem. So that's our reason why. If we had to give a reason why we could do what we just did, that'd be it. Okay, so now let's actually solve for the variables. I didn't tell you that that's what we were doing here to start, but let's solve for the variables. I could easily say, now that I've drawn that, hopefully you could easily say this too, that remember, if you add the 3 interior angles in a triangle, you should get 180 degrees. So let's solve this for x from here. I've got 2x plus 75. That equals 180. And I'll use my orange here to show these intermediate steps. These are steps that if you get good enough at it, I feel like you can leave those out, but good things to write in though. So let's now see what we got here. This cancels with this. You got 2x equals, that'll be 105. And so now we take this, we divide it by 2, and we have our answer. This one's not going to be a nice pretty whole number. It's going to be x equals, and this will be 52.5. So 52.5, you could say 52.5 degrees, but the degree symbol's already in there. X kind of represents the number that goes before the degrees, so I'd take that either way. 52.5 degrees, or just 52.5 right there. And so what would y be? Well, if this is x and this is x, I hope you can see that that's the same thing over here. And so these two angles match up with these two angles. I could go back to the third angles theorem actually and say that if the two angles here are congruent to two other angles over here, the third angles have to match up. So I'm going to say that y equals 75. You could also say 75 degrees based on that. So y equals 75 by the third angles theorem. So that would be my reason I would give if I had to give a reason right there. And I felt like it would be valuable to open up the 4.2 finish note. So here was the third angles theorem, just to remind you of what that said. You had two angles matching up with two angles in triangles. You can say that the third angles also match up. So that's exactly what we had here. We had two angles here matching up with two angles here. That means their third angles match up. Could I also say that this and this add to 105 and then do 180 minus 105, giving me that as 75? Sure, that would also work as well. So you could do that either way. So sometimes a couple different ways or multiple ways to do the same thing, valid ways to get the same sort of thing. Alright, so now it's time to explore essentially what is our last possible combination of letters. I had side, side, side. We've already determined that angle, angle, angle doesn't work. We'll talk more about that later when we talk about angle similarity, but angle, angle, angle doesn't work because you can basically just blow up a triangle, make it bigger, but the angles don't change. And so we had side, angle, side. We had angle, side, angle. We had angle, angle, side. But this is another combination where you have two sides and an angle. So is this a possibility? Does this work? So let's explore this one a little bit. Don't copy these pictures down yet. I will have you copy something down in a little bit. But let's see if this works. So you may be saying, well, they've all worked before. I think this one's going to work too. Let's try. Maybe you're right. Maybe you're not. Well, let's figure this out here. So let's see what we got. So I'm going to take this, and this has to be true. Notice I have this side, and a non-included angle here. That's what this means in this order. So a side, a non-included angle, matching up with a side, and a non-included angle. Now I can't change the angle. I can't change the length of these sides. I could change this angle right here because that's not rigid, but all these things, the arc marks the angle here is not going to change. This is rigid, this angle, these two side lengths are rigid. This green length is not rigid, so I'm going to pull that out, and boom, there I got this one set up to make a nice easy triangle like that. This is one possible triangle I could make with that. Now let's do the same thing over here, and well, I could kind of flip this around, rotate it. So at first glance out, it seems like, yeah, this is the same thing. Why are we doing this, Mr. White? Oh, wait, whoa. Okay, do you see what I see? Oh my gosh. It finally didn't work. Take this around. Okay, did I just change the side length of that one? No, I did not. And whoa! finally got one. All right. So, is this triangle congruent? I didn't pick up my pen. Come on. Is this triangle congruent to this one? Absolutely not. But is this the same? Side, side, and angle. Is that the same as this side, and this angle? Yeah, it is. So is this a theorem? No, it is not. So this one, side, side, angle, I just came up with what basically is a counterexample. So I want to write that down, that there is no side, side angle. This does not work. There is no side, side angle. And let's copy the picture down now. If you haven't done that yet, copy this picture down. Make sure that this kind of sticks out farther this way. And what am I saying had to be true to start? I'm saying that these had to match up here. I'm saying that this had to match up here with this one. The lengths had to be the same, and this angle had to be the same as this one. But notice this green side, that wasn't rigid. This angle was not rigid. And so I could essentially swing this like a door hinge, like a door swinging on a hinge. This could go over here, and I could have another triangle like that. So this is a counterexample. So let's write that down too. This is a counterexample. So if you can come up with one counterexample to a conjecture, this is kind of our conjecture that we thought this would work. So this is a counterexample. It does not work. What's an easy way to remember this? Okay, how can I remember that this is the one that doesn't work? I want you to not write this down, but spell it backwards, okay? Alright, there, start here, okay, then there, and then there. Alright, that's not a word I should hear in class. That's not a word I want to see you write down on the paper, and that's not a theorem for us either. How convenient that that works out that way. Very, very nice. Okay, so there is no ASS theorem. If you spell it the other way, SSA, there is no SSA theorem. Okay, so this is a counterexample to that. But does it work in some cases in a sense? Let's check out a different case where something else is being true. So let's explore what I'm calling hypotenuse leg. So now I have the same sort of thing going on. The blue part, the red part, and the green part that's drawn in there. This can't change. This side length can't change. This angle could change right here, but these two side lengths have to be rigid, and this angle has to be the same too. So I have a hypotenuse, the blue part's the hypotenuse, and I have a leg right here. Can I change this green length? Yeah, well I have to make a triangle eventually, so this is going to have to change. But I'm saying, could I rotate this around? Could I, in a sense, move? I don't want to change the length, so I don't want to pull that one. But could I rotate this around and kind of move that over here? Sure, but notice, I'm not going to be able to make a triangle anymore. So I can't now connect this, because this is a rigid angle at this point. I can't take this and still make it 90 and pull it down here. So let's undo what I just did there, and let's see what we got. So let's take this. I'm going to pull this all the way over. And okay, so that's one possible way to make the triangle there. What happened there? There we go. And is there another way to do this? Well, I could take this out. I could extend it. Let's extend this a little farther, and let's see what we got here. Anyway, I can take this blue part, and I know I couldn't rotate it like I did, because then I'm not going to be able to make a triangle anymore. That doesn't work anymore. So I'm going to undo that. That's no good. I want to redo that one though. Okay, there we go. And so I don't know why that's doing that. There we go. So if I could do that, can I extend this out this way and make a triangle that way? Well, no, because I just changed the length of that, and I said that was rigid. That can't change. So I got to undo that too. And so I could keep maneuvering stuff around. Can I change the length of this red part? No. Could I pull this in this way? It's not wanting to go this way. I know why, because I made that a vertical one. But could I take this and pull it in this way? No, because that wouldn't be a right angle anymore. So that's not going to work either. So is there another way to draw this triangle? There is not. So we actually in a sense have a side-side angle, but it has to be a side-side angle where the angle in question is a right angle. So we say that we have this as our fifth and final congruence theorem or postulate for congruency of triangles. Let's draw this in at this point. So have this drawn on there. I want to make that blue just a second. So let's have this drawn in on here, that this and this are congruent. The hypotenuses, hypoteni, I think it's hypotenuses, are congruent, and the leg, one of the legs, are congruent over here. So this is, in a sense, side angle, but the angle has to be a 90-degree angle. It has to be a right angle, side angle, but again, the angle has to be a right angle. So this is another theorem for us. So this is called the hypotenuse leg, and from here on out I'm just going to be saying HL, but that's what the H and the L stand for. So hypotenuse leg theorem. This is theorem, congruence theorem. You know what, I don't even know the number of it, so I just looked at it in the book just to double check that, and it's theorem 4.8, which would make sense because we just did theorem 4.7. That was the most recent one prior to that. So this one, I just want you to say HL from here on out. What is the HL congruence theorem? It says that if the hypotenuse and a leg, remember there's two legs to a right triangle, but hypotenuse and a leg of a right triangle. So to have a hypotenuse, you have to have a right triangle. That would make sense that I would say right triangle. Hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of another right triangle. They both have to be right triangles of another right triangle the two triangles are congruent. And like magic, a bathroom on an airplane appears. What do you call, sometimes another name for a toilet is a pot. What do you call a bathroom being used on an airplane? It's occupied. What do you call that? You call that a hypotenuse. Anyway, the five triangle postulates or theorems that we have. This is big. This is boxed in. This is huge. So this is basically the recap of what we've been learning for the past, what, like 3 or 4 lessons. The big kahuna, you might say. The big synopsis. Side, side, side. That was number 1. Do you remember the next one? If you said side, angle, side, you got it. Do you remember the next one? Angle, side, angle. How about the next one? The next one was angle, angle, side, and then finally we just learned the 5th one. The 5th and final one is HL, hypotenuse leg. So this is big. You gotta know these 5 things for the quiz. You gotta know these 5 things for the test, for the benchmark. You gotta remember those 5 things. Okay, so let's do a proof example here, and we'll get to this part in a second. We're going to have some fun with that. But let's draw on some things here. Take out your different colors again. Right now we're going to start with pencil. We're going to add some things in here in the picture, just in pencil, the normal thing we've been writing with. So copy the picture down, and I want you to add some markings in the picture like this. We're going to say this side's congruent to this side. We're going to say that this side, this segment's congruent to this one. And we're also going to put in a couple more things. We're going to say that this is 90 degrees, this is 90 degrees, and that this is parallel to this. Okay, so what am I giving you? I'm giving you a lot in that picture. And I'm going to say, see below. We will write down all the given stuff in the proof below there. And what do I want you to prove? Well, I haven't given any labels to the letters to the vertices here that I see. So this is what I got here. T, A, R. Let's say this is E, this is Y, and this is L. Alright, so we've got our 6 letters here, and I want you to try to prove that angle T is congruent to angle L. So let's make our, it's not a funky L, it shouldn't be a funky L, there we go. Let's make our 2 columns. I want to make that red though, let me do that. And boom, alright, so we've got our 2 columns there. Here's going to be my statements column, here's my reasons column. Number 1, step 1 is given. And what is given in this picture? There's quite a bit. So let's see what we got here. I could say that RE is parallel to AY. Could I call AY, could I say that's TL or TY or AL? Sure, I could say any of those things. But I'm going to go with RE is parallel to AY. AY includes T and L if I extend that out as a line instead of that segment. But this is true. What else do I have being true there? I also have that I can just look at the picture and see that TR, segment TR is congruent to segment LE. You can also see that segment TA is congruent to segment YL. And I can see that I have 2 90-degree angles as well. I'm going to say it like this, that RE, what's that symbol mean again? Upside down T, that's perpendicular. So RE is perpendicular to RA, segment RA. And I also have that RE is perpendicular to segments YE or EY. Either way would be fine. So I got all that stuff being true to start. Okay, so different color time. Take out that different color. I need to see different colors on the notes here. So I've got this angle, this angle. Well, I have a parallel line here to a parallel line here. I've got a transversal here, and I've got another transversal over here. So I see some different things I could say here. I could say even that this one and this one are consecutive interior angles. They're supposed to add to 180. So I could put a right angle right there. But really, where I want to go with this is to prove that this triangle here is congruent to this triangle here. So if I said something about this angle, that really doesn't get me as far as if I could say something about this angle. So I know that this one and this one are alternate interior angles based on these being parallel lines. So I could say that this one and this one are congruent to each other. And I could say the same thing over here, that this one and this one are congruent to each other. It just happens to be 90 degrees, which is convenient for me. In this case, we'll see why in just a second, but let's write down step 2 here. So what's the reason for angle TAR being congruent to angle ERA? So you can say that. And what's the reason for angle LYE? Angle lie. I've spelled 3 different words here already. Tar, era, lie. Hint, hint. I'm getting to that later. So angle lie is congruent to angle REY. Why would that be true? Okay, well I could say that's true. We just said it. Alternate interior angles. They are alternate interior angles. Alright, so what can I say now about, I guess I don't need another color yet there, but what can I say looking at this triangle, triangle RAT, triangle RAT, and triangle LYE, triangle Y. What's true about those? Do I have what I need? Do I have one of these 5 things right here? Do I have side, side, side? No. Do I have side, angle, side, or angle, side, angle? That's not what I see. What I see here is side, side, and non-included angle and side, side, non-included angle. Oh man, can't do it. Side, side angle doesn't work. But hold on. Side, side angle, when that angle is a right angle, which is what we have here, when that angle is a right angle, then we call that hypotenuse leg. So I have a hypotenuse, that's this side right here, and I have a leg matching up with a hypotenuse and a leg in this triangle. So I can certainly say that the triangles are congruent. And I'll go with rat. Triangle rat being congruent to triangle lie. But I want to make the congruent statement correct. So RAT is going to be the same as triangle EYL. I better go in that order. I will be checking for that. I'll be looking for that. Got to have those congruent statements matching up. The letters have to match up in the proper order. And so why is this true? This was side, side angle in a sense, but it's that special case. We can't use side, side angle. We can't spell it backwards and have a word that I want to see. That shouldn't be on your paper ever. You shouldn't hear it out of your mouth ever. Professional language in the classroom. Thank you. So we can say HL, hypotenuse leg. And now that that's true, this yellow thing, let's not put this in our picture, in your picture, but I can put that here. I'm going to say that this angle right here matches up with this angle right here. And why was that again? Why could we say those angles are now going to match up? Because, well, let's write that down first. Angle T is congruent to angle L. Do you remember the corresponding parts of congruent triangles being congruent? That's what we're talking about. Corresponding parts, CP, of congruent triangles, CT, are congruent. Corresponding parts of congruent triangles are congruent. CP, CT, C is what we have right there. And so just for fun, if you want to, I'll take the top 3 in each class. How many words can you spell with the given 6 letters? What am I talking about by that? Let me extend this out a little bit. So I'm saying, like, well, let's start with this one here. I'm going to say that you have to have at least 2 letters in your word. Like A doesn't count. So at least 2 letters. I could spell the word at with the 6 letters in here. I could spell the word ear, E-A-R. I could spell a lot more words. I'll just do one more and then let you go at it as well. So R-A-T, rat. So that's going to be my list. I'm going to keep going if I can. How many can you spell? We'll make a little challenge out of it just for fun. If you want to participate in that, bring that to me on a separate piece of paper, not on your notes, but on a separate piece of paper, and give that a shot with these 6 letters, the R, the E, T, A, Y, and L. But hopefully you found that helpful, and as always, let me know if you have any questions in class, if something didn't make sense to you. Thanks, and have a great day.